Okay, so this is problem number 5 from the same homework. This is a slight play on actually one of the problems that we've done earlier. So slight twist of it. So you're given X and Y, which are uniformly distributed inside this annular region. So inside this annular region that you see in this here. So inside this region, this is where X and Y are distributed, okay? And uniformly distributed, right? So this is the same height up top, okay? I know that the inner boundary is 5. So R1 is equals to 5. So I know that R1 is equal to 5, whatever that unit is, actually 5 meters. And R2 is, the outer boundary is 10 meters, okay? And now I want to compute, let's say a body or a robot, for example, was a sensor in this case. And this is actually a problem that I looked up while I was reading one of the papers on sensor networks. So the sensor is uniformly distributed inside this annular region, and we're required to find the PDF of the distance from the origin, distance of this sensor from the origin. That's what we're required to find, and we're also required to find the PDF of the angle that the vector makes if you join the origin to the sensor, right? So the angle of the sensor from the origin, okay? So that's what we're required to find. And the way we're going to go about this is very, very similar to all of the examples that we've done in class. So I'm going to do the problem, so the part A first, where I'm required to find the PDF of R. And I'm going to start out with computing the CDF first, right? So this is F R of R, small r, is just simply equal to the probability that capital R is less than equal to R, which is the probability that X squared plus Y squared is less than equal to R. And in order to compute this probability that X squared plus Y squared whole root is less than equal to R, all I need to do, I need to compute the volume, if you will, under the joint PDF, right? So I need to integrate the joint PDF of X and Y over the region which satisfies this condition that X squared plus Y squared is less than equal to R. And so this is fxy, xy, dx, dy. And I know that fx of y, this joint PDF of x and y, is equal to 1 upon 75 pi, only in the region where this x squared plus y squared root is less than 10 or is greater than 5, between the radius of 5 and 10 meters, okay? And that ensures, KG, this must be x squared plus y squared is less than equal to R, and this must be greater than equal to 5, because otherwise, because if it's less than 5, this must be equal to 0, right? And for this integral to hold true, R therefore must also be less than 10, right? So because if it's greater than 10, then this integral or this mathematical form will not hold true. And actually for R is greater than 10, the CDF must saturate to 1. Okay, so that should be very, very clear. Okay, so all we need to do therefore next is to compute this integral. Okay, so that's what we're going to do next, right? So we're required to compute this integral, which is 5 is less than. So I'm going to bring out the 75 pi here, and this is 5 is less than equal to x squared plus y squared is less than equal to R times, and this is what I'm integrating. And you could, if you want to, go from the rectangular coordinate to the polar coordinate system, and that's a valid thing to do. I would rather just look at this graphically. And what we're required to find here is to find the area of what this is, just the area of an annular region, which is which looks something like this, right? So this is, let's say, if this, so what we're required to find is if this distance is 5 and this distance is r, we're just required to find the area in this region, right? That's what this integral represents, okay? And I know that this area is equal to nothing but pi times r squared minus 5 squared, which is 25, right? So this is the area of this annular region, okay? So therefore, this turns out to be equal to 1 upon 75 pi times r squared minus 25. So this is the CDF. Let me write this down here just to clarify that what the limits are. So this is the CDF of r, which is equal to 1 upon 75 pi, and the pi cancels. So this is r squared minus 25. And this mathematical relationship holds true only when r is between 5 and 10, right? That should be clear, right? And it's going to be equal to what? This is going to be equal to 0 for all values of r which are less than 5, and is going to be equal to 1 for all values of r which are greater than 10. Okay, so this is the CDF of r. In order to compute the PDF, all I need to do is just to compute the integral, or sorry, the derivative of the CDF. And that turns out to be equal to 2 times r upon 75, only for the case where r is in between 5 and 10 meters, right? So I can just simply say this is u of r minus 5 minus u of r minus 10. So this is the PDF for the radius of radius of the sensor, of the distance of the sensor from the origin. Okay. Now let's do part B. Part B is just asks you to compute the PDF of the angle of the sensor from the origin, right? So we have theta equals tan inverse y by x. So we're required to find the PDF of theta. In order to find the PDF, I just start, as I did earlier, with the, so let me use capital theta here to represent that this is a random variable, and this is a small theta to represent this is actually the variable at which the CDF is being evaluated at, right? So this is just simply equal to the probability that my random variable is less than equal to this small theta. This is nothing but the probability that tangent inverse y by x is less than equal to theta. And in order to compute this, I will just simply go about exactly the same principle. I will integrate the PDF of x and y, right? So the PDF of x and y, the joint PDF of x and y over that region that satisfies this condition, tangent inverse y by x is less than equal to theta. And here, all right, so I will make a change of variables. I'll go from the polar coordinate system from the rectangular coordinate system to the polar coordinate system. I could do otherwise as well, do it graphically as well. Let me use the conversion from rectangular to polar. So dx dy is r times dr times d theta. And by the way, I mean, when you say tan inverse y by x is less than or equal to theta, what you're actually doing is, I know that the PDF is between 5 and 10, okay? And so this is the x-axis. And so let's say if this was theta, right? So what you're required to do is you just need to compute this area, right? This area is actually equal to the probability that tan inverse y by x is less than equal to theta, right? So where this is the angle theta that we're talking about, and theta could go from 0 all the way up to 2 pi, right? So that's what you're required to do. You can use direct formulas if you will. That's possible. I am going to instead go about it with that conversion, with following all the steps. Okay, so the radius goes from where to where. Radius goes from 5 to 10. This goes from 5 to 10, and the angle goes from where to where. Angle goes from 0 to theta, right? And this is the integral I wish to compute. Okay, so the integral is the following. So this is, and you see r and theta are once again separable. So this is 1 upon 75 pi outside. This is integral from 5 to 10 r times dr, and then this is integral from 0 to theta. You're integrating theta. So this is r squared by 75 pi times 2, integrate, evaluated where 10 to 5, and times theta, and this is 100 minus 25 divided by 75 pi times 2 times theta, and this is actually the numerator 75 as well. That 75 cancels with 75, so this is nothing but theta upon 2 pi. So this is my joint, the CDF of the random variable theta, and of course this is only valid where for theta ranging from 0 to 2 pi, and so this is the only region where this functional relationship holds. Okay, and therefore this implies so f theta, or the PDF of theta, is just simply the derivative of the CDF, and this turns out to be equal to 1 upon 2 pi. Only when 0 is less than theta is less than 2 pi, and is 0 otherwise. So therefore theta is still uniform, right? So the angle is a uniform random variable, is uniformly distributed between 0 and 2 pi. On the other hand, r, let me go back. So r is this distribution here. Okay, so r is not uniform, is only distributed between 5 and 10. And has a sort of a ramp, if you will, is a ramp PDF. Okay, right. So that was problem number 5.